All right, hello everybody. My name is Ryan. I'm joined by my colleague Karthik, and we're both from the worldwide specialist organization within Amazon Web Services, and we focus on DocumentDB. And today we're going to talk about case studies and best practices. So on the agenda, we'll talk a little bit about what is DocumentDB. I'll talk through some case studies, and then I'll hand it over to my colleague Karthik to run through the best practices. So before we dive deep into DocumentDB, just want to take a step back and show you guys the broad array of services that we offer across databases and analytics. Within databases, we have two primary categories. One is the relational databases, and the other is non-relational databases. And DocumentDB falls under the non-relational databases. The other services on the right fall under our analytics portfolio. And it's important to note that with databases in particular, we offer what's called a purpose-built database. And what that means is our database is specific to your use case, and the service that you use will typically correspond to that use case. So keep that in mind as we go through the presentation. Another important note is that according to IDC, 90% of data being created right now is unstructured. So this growth has really led customers to choose the purpose-built database for their respective workloads. And as a result, the global non-relational market is currently witnessing a 30% compound annual growth rate from 2020 to 2025. And it's expected to grow from 2 billion to 22 billion in that time frame. And within this category, document databases holds the second largest share and the fastest growth rate. So very, very up and coming, a lot of high demand for this service. All right, so what is DocumentDB? It's a fully managed, scalable document database service that supports MongoDB workloads. It's fully managed, and there's no hardware to provision. It's very easy to set up through the console. You can spin up a cluster in minutes. We have built-in high availability. Clusters are automatically provisioned across multiple availability zones. Our best practices are enabled by default. So for example, backups are enabled. You get durability built in. We copy data 6 ways across 3 AZs. And then for security, you can use identity and access management as well as built-in role-based access control to enforce least privilege access. Patching and maintenance are handled automatically by the service. And then we have native integration with other services such as CloudWatch for monitoring and setting up alarms, CloudTrail for logging and auditing, and other services that really help simplify your tech stack. Our customer FINRA utilizes DocumentDB without any overhead from their engineering teams. DocumentDB is scalable. We have a unique architecture. The separation of compute and storage allows you to scale both of these aspects independently. You can scale compute horizontally or vertically in minutes, regardless of the amount of storage in the cluster. Storage and I/O auto-scale from 10 gigs up to 64 terabytes, so there's no need to worry about taking care of an EBS volume or scaling an on-premise SAN. You can scale out to 15 read replicas in a matter of minutes. And our customer Iron, they like DocumentDB because they can scale their clusters in minutes, regardless of the amount of data in the cluster. And finally, we're MongoDB compatible. So we're compatible with 3.6 and 4.0. We use the same SDKs, tools, and you can use the same application as you currently do with Mongo. We support hundreds of APIs, operators, and aggregation stages, and we work backwards from our customers. We start with you, get feedback on the product, which is then fed back into our engineering teams to implement feature requests. Our customer Freshworks love the fact that we are compatible with MongoDB. Their application requires 0 code changes. Now, when should you use a document database? Probably the biggest use case is around JSON data. Document databases store data in a JSON-like format, which is flexibly structured and really maps naturally to how we think about modeling data in our applications. We really don't think about modeling data in a tabular format like you would with a relational database, but we're thinking about groups of things instead. Whenever you have a requirement for a flexible schema, with document databases, there's no need to design a complicated or rigid schema up front. The schema is flexible. It can change depending on our data needs and our access patterns. Whenever you're looking for ad hoc querying capabilities, whenever you need to retrieve specific fields and values, and maybe even work with regular expression queries. DocumentDB uses a JSON-like query language, so it's really easy to learn. And when you're looking for flexible indexing, indexes can be created and dropped on demand, and can be declared on any field within your documents, including fields nested within arrays. We have a whole lot of customers that are utilizing DocumentDB since we've been GA in the marketplace now a little bit over 2 years. They're running anything from POCs to production level workloads. And these span the gamut, anywhere from small startups to Fortune 50 customers that are using DocumentDB for their production workloads. Use cases, so content management, a lot of the content that we read today, from news articles to blogs to recipes to patient records, all of that data lends itself really well to a document model since it's dynamic and changing. Mobile is another great use case. It's very easy to store the data you're collecting, going back and forth between devices. Catalogs, being able to record the outputs of machine learning experiments, inventory descriptions, pharmaceutical trials. We see a broad set of customers that use document databases for these use cases. And then gaming, storing user profiles, game management, matchmaking. Anytime you have a complex document that's dynamic and changing and may require ad hoc querying, indexing, or aggregations, that's really a good indicator for a use case for DocumentDB. I want to transition now and talk a little bit about our case studies. And the first one I'll talk about is Rappi. This is a Colombia-based startup, very similar to DoorDash here in the US. This is an app that handles restaurant orders, groceries, and even clothing delivery. Their business problem was that they had a really popular delivery service, and they were experiencing a lot of outages. Sometimes these outages lasted anywhere from 3 to 4 hours during the peak service times. They built a monolithic application and needed to support a move to a more flexible and microservices driven approach. And then in addition, they had slow performance. So this affected thousands of users, and queries sometimes took as long as 500 milliseconds. So their requirements were compatibility with MongoDB. Their engineers were very familiar with MongoDB, and so this was an important factor. They wanted to independently scale microservices. Again, I talked about the monolithic architecture. They had one Elasticsearch cluster for all of their 9 business units for each of their countries. They wanted to get out of the infrastructure management business and eliminate what we often call the undifferentiated heavy lifting of maintaining infrastructure for their multiple MongoDB clusters. So their solution was to create a single cluster per business unit, and this gave them the ability to scale their microservices. And then in addition, the solution has horizontal scaling of read workloads, which reduced their query latency from 500 milliseconds down to 80 milliseconds, which was a nearly 16x reduction. And then with minimal code changes, they were able to migrate from MongoDB to DocumentDB, resulting in a 60% FTE cost savings. And then the solution advantages. Prior to this solution, I mentioned Rappi had faced a lot of outages due to scaling and performance. Since implementing DocumentDB, they've had 0 outages. Their largest cluster took 2 weeks to migrate, but they were able to, after they did that migration, they were able to perform over 100 migrations in less than 3 months. And most importantly, Rappi right now only has a handful of engineers managing the DocumentDB deployment compared to the dozens that they had before. And this allows their teams to focus more on value-add activities. The second case study is for Zulily. If you're not familiar with Zulily, they're an e-commerce website. They offer product deals for moms, kids, and babies. And their business problem was a little bit different. They had a problem with search. Their current search experience lacked the ability to offer suggestions or relevance. It was really difficult to maintain. So they really wanted to deliver enhanced customer-focused search experience. Search was the #2 most used feature on their website and on the app. So the requirements for around search were fourfold. Suggestive, the search needed to share with customers what was currently trending. The search needed to be relevant. So Zulily displays products for up to 3 days. So afterwards the products disappear, and so they need to suggest something that's available and in inventory, and that checking in the back end has to happen in real time. The third requirement was around diversity. So Zulily carries brands from national brands as well as some well-known boutique brands in their catalog. And then finally, the search needed to be personalized. So they need to display content that's relevant to the individual user. So their solution offered a data flow that search first started with extracting search keywords from clickstream. This can include anything from customer visits to assets that were clicked while browsing or any links that were clicked. They then correlated those search results to the related brands and categories to make the search richer and more meaningful. On the back end, they would check that search with the current inventory for availability, since remember, these products disappear usually within 3 days. And then they persist the results in a fast data store where they can then be displayed back to the user. What's really cool about this solution is they use multiple AWS services. So Kinesis data streams, Kinesis data analytics, Lambda, as well as DocumentDB for the backend data store. And then they also took a microservices approach, which gave their engineers the ability to maintain and manage different services independently. One big trade-off that they discussed during the solution aspect was the design considerations. Do their engineers want to spend more time managing Mongo, or do they want to become a search expert? An overwhelming response from the engineering team was, we want to be search experts. So solution advantages. 3/4 of customers chose to utilize this enriched search function. So they had greater adoption and acceptance of the new feature, which then translated into an uptick in revenue. The enhanced search also allowed for a better customer experience, since now they're able to check inventory on demand before it actually disappears and before they actually suggest it to their customers. And then from a time to market perspective, they were able to reduce that time from 16 weeks down to 10 weeks. So just to finish things off, why Amazon DocumentDB? We can handle up to millions of requests per second. We already have many customers already running production level applications since we GA'd over 2 years ago. You can use the same code, drivers, and tools that you use with Mongo. It's very simple to migrate your existing applications. You can build globally distributed applications using our new global clusters and cross-region replication feature. This gives you the ability to have fast access to local data as well as disaster recovery capabilities. It's very simple and easy to manage. You no longer need to provision hardware, and all of the patching, configuring, backups, scaling, very easy to handle with a click of a button or an API call. And then we're secure and compliant. Data is encrypted at rest and in transit. We have a global presence. We're highly available. Data is replicated 6 ways across 3 AZs. You only pay for a single copy, and the other 5 are available for free for durability purposes. And then probably the most important, we're deeply integrated with other AWS services, CloudWatch for monitoring, VPC and Secrets Manager for security, and many more. And with that, I'm going to pass it over to my colleague, Karthik, who will talk a little bit more about DocumentDB best practices.
Thank you, Ryan. Hey all. In this section of the presentation, I will discuss 5 best practices for DocumentDB that are commonly implemented by our customers. These best practices will help you build applications with optimal performance, reliability, and also give you tips on saving cost. Let's start with how to connect to Amazon DocumentDB from your application. We recommend that you connect to DocumentDB cluster as a replica set and use read preference as secondary preferred. This will allow you to scale your reads by leveraging the read replicas while allowing the primary instance to focus on handling writes. DocumentDB's architecture segregates storage and compute, and also the durability is offloaded to the storage layer. This allows you to use the replica instance. Again, when you use the read preference as secondary preferred, you'll be able to use the replica instance to scale the reads, and especially when you have complex analytical queries, you would not be impeding the durability anymore, because those long-running analytical queries are not going to block the writes, because you're segregating the read and write traffic efficiently by using these settings. And also from a security perspective, we recommend that you restrict DocumentDB security group to allow inbound access over port 27017 using the TCP protocol, only for the specific applications that are allowed to interact with DocumentDB. This will limit the surface area of attack, and will help you make your DocumentDB configuration more secure. And when it comes to the credential management, right? So DocumentDB, being a native AWS service, integrates with Secrets Manager. And the application, as you see in the slide, will provide a secret name when calling the Secrets Manager API, and in return, Secrets Manager will give you the credentials to access DocumentDB. You can also leverage the out-of-the-box Secrets Manager capability to rotate credentials if that is of importance for your enterprise. It's a recommended practice to use the Secrets Manager integration to manage your database credentials. So again, this is out-of-the-box integration, benefit of using a native AWS service. So if you put this all together, how does that look in terms of a code, right? So this sample code demonstrates how you can connect to DocumentDB. So as you see, I've just highlighted some key areas that we've covered so far. So you can retrieve the credentials, like the host name and the port details from Secrets Manager, and then use replica set. This RS0 is a standard default value. It's a constant, and that tells that you're connecting as a replica set. So when you use RS0 to connect as a replica set, and then use the read preference as secondary preferred, which was the second point we discussed a couple of slides ago. And this will allow you to scale the reads across the replica instance. So this is like putting all the things together. That's what you see in this slide. So let's take a look at this code that we just saw in action in this demo. So here I have a cluster called Getting Started with DocumentDB, and I have the sample code that I just showed to you in the sample app.py. It's exactly the same code, getting it from Secrets Manager and then using those values to connect. And then all that it does is it's a very simple app that inserts data into DocumentDB. So let me go back to this terminal here, and I'm going to run this sample app.py. There you go. So it shows that I've connected to DocumentDB, and I also successfully inserted data. Document X, Amazon DocumentDB, is inserted into the database, and the object ID was automatically created. All right, so let's push along this presentation, right? So now let's go to the second best practice. We saw how to connect to DocumentDB. Let's now discuss the best practices around indexing strategy and query tuning. Let's start with the indexing in DocumentDB. We'll look at it from a design, build, and use perspective. When it comes to designing the indexes in DocumentDB, unless you're running an analytical query with no strict SLAs, every query should use an index. It's a best practice to limit the number of indexes per collection to 5 or less. And then to identify the appropriate fields that you should be using for indexing, I would suggest that you rank all your queries by the frequency at which they are called. Like look at your queries per second and identify the common filtered fields. And when you're creating indexes, you can create simple or compound indexes. And when you're using compound or creating compound indexes, use the most selective field as the first field in the index, as this will help to narrow the search or basically filters more document upfront. And we strongly recommend that you create indexes on fields that have high cardinality, because this helps with high selectivity of the documents and ensure that the fields that you index on narrow down the document search to less than 100 documents. This will again help with the very optimal performance for your queries. Compound indexes generally work well when fields appear together in the queries, right? But if the fields are used individually, generally multiple single indexes are a better choice. And when you're using compound indexes, it is possible to do an equality or a range query on the prefix or the first field in the compound index. And if you have sort operations in your query, you can also add that field on which you're sorting as a suffix field onto this index. Compound indexes generally have higher cost, I'm talking about performance cost here, than simple indexes. So you may see that the optimizer will pick simple indexes over compound indexes if they exist. So again, another best practice, and I'll talk about it in a bit as well, is to remove your unused simple indexes, or any unused indexes for that matter. Use the hint option to select compound indexes. Now, when it comes to building an index in an ideal scenario, we would like the total index to fit in memory. If you see that the total index size comes close to or even exceeding your collection size, that's an indication that you have either way too many indexes or inefficient indexes. And when you create indexes on very large arrays or long strings with very few unique values, it can result in index inefficiencies. DocumentDB uses a B-tree data structure for storing indexes. And when you create indexes on fields with those unique few unique values, like I was mentioning a moment ago, this will result in a very deep B-tree scan. And one way to reduce the index size and improve performance in these scenarios is to use string interning. This may not be applicable for every use case, but that's one workaround if it applies to you. String interning is basically mapping unique strings to integers and storing those integers in DocumentDB instead of the strings. Think about Java applications where you have the string to enum mapping. It's a very similar concept. Right, so that's for situations where you have large arrays and long strings with few unique values. When it comes to using indexes in DocumentDB, it is important to understand that the query optimizer uses index stats for each collection and analyzes the query parameters to select appropriate query plan. The optimizer may choose to do a collection scan over index scan based on these stats, the index stats that I was referring to. Let's say, for example, you've created an index on a field that is not selective, it's not highly cardinal. Then performing a collection scan may be cheaper for the optimizer than the index scan, and hence it may choose to do a collection scan. And you can determine what the query optimizer, what query plan the query optimizer is going to be selecting by using an explain plan on the query. It's just an explain off, and I'll show this to you in a demo here. This information will be based on the stat at that point in time when you're running explain. And you might want to use hints to force an index selection if the correct index is not selected by default. Consider scenarios that we just discussed where you have both simple and compound index, and the optimizer is picking simple index, but you wanted to pick compound index. You can use hints to do so. Now, let's talk about query tuning, right? When it comes to investigating slow query performance, start with the query plan, right? Use the explain stats to see the chosen query plan, determine how much time that query is spending in each stage. You can see an example on the right-hand side of the screen, right, where you read it inside out, right? So on the innermost thing over here is the collection scan. The innermost stage is the collection scan. It retrieves about 250,000 documents. It takes about 466 millisecond, and then the aggregate stage adds on about 20 milliseconds to it, to 485, and so on, and the total time is 486 milliseconds. So you can use the stat and see where the query is taking more time. In this example, the query is taking significant amount of time because it's doing a collection scan. So again, an opportunity to optimize by creating appropriate indexes. So you can use explain plan to see those stats, or you can enable slow query profiler to capture all the queries below a specific threshold in the cluster parameter group. You can use the db.currentOp command to return all running queries, and it will also tell you if a query is blocked or waiting on something like logs or wait states. And when it comes to query execution, I always like to visualize the flow. Basically start from the index, see how many documents did the index match for a given query. And then organize the query. On the right-hand side, I've given an example of what I'm explaining here, right? Organize the query to filter more documents upfront. Again, if you use match operator, and then in this case, I'm matching on a name, right? So if you're using match and filtering upfront, you can obviously create an index on that name attribute. This will help filter more document upfront. And then transform the information that you do not need for this query. For example, using a project operator, as you see here, you will use the fields that are required by the query, but also on the hindsight, it will not use the other fields, so that any further stages of the aggregation pipeline will have less data to work with. And then when you're using accumulators, if at all your query uses those, like min-max kind of accumulator, $min, $max, they are cheaper, but $group and $sort are generally expensive, and they may be using disk. For example, $sort may use the disk, but $min can finish that computation in memory. An accumulator generally requires all the documents that are scanned to be read before it can move to the next stage in the pipeline. And when there are large documents, there will be spilled to disks, and hence reducing these documents upfront by using those match and project really helps, with query performance. So, and also, like if you're when the disk is being used by these queries, you could see a metric called free local storage, and it will drop, right? And if that happens, see if you can use hint and see if you can select an index that will perform a hash aggregate versus sort aggregate. What is the difference between the two? Hash aggregate happens in memory, sort aggregate happens on the disk. So if you have more efficient index that can perform aggregation operation at the memory level, then probably use hint to select that. So now it's demo time again. In this demo, I'll show you how you can use the explain plan, and I'll also show you how you can tune queries by creating appropriate indexes. So let me clear the screen over here from the previous demo, and I'm gonna connect to DocumentDB. So I'm gonna go to DocumentDB over here. I'm gonna copy this, and I'm gonna come back to this, paste it, and I'm just gonna say good, and then here I'm gonna say show DBs. You can see that I have the test was created in the previous demo where we inserted one document, and I can see I have a couple more databases. So I'm gonna use the first database. Feels odd to say use COVID, but that's the database I'm gonna be using. And now here, if you look at this database, if I say show collections, you would see that I have like a collection called daily cases. I'm going to run a simple query here to show how you can use explain plan. So I'm going to say run this query with explain plan, and I'm passing this execution stats as parameter. And you can see that this particular query is doing a collection scan. So always read inside out. It does a collection scan, and then it takes like whatever 4.004 milliseconds, and it takes like 0.192 in total as the execution time. Right now, I'm gonna instead of just doing a find and limit, I'm gonna run some more realistic queries here, right? Like for example, I'm trying to find, I'm querying this collection to find in this province and for this user, what are the cases, and I'm sorting these by attribute called cases, right? So if I'm just running an explain plan on this again. So if you look at this explain plan, it again performs a collection scan because I don't have any index, and this is performing a collection scan. And it takes about close to 280 milliseconds, and the overall time. So it's of the entire 279.67, 279.31 is spent creating, in the collection scan. So how can I optimize this query? Now I know that the bottleneck is because of the collection scan. So what I'm going to do now is I'm going to go ahead and create an index on, the few attributes. So if you recall from the last slide, I was telling how you need to find the right attributes and create index on them. So the query was on province, state, and admin too. And also there was a sort on this cases attribute. So I'm adding that as my, as my suffix, and the other, like the province, state as my prefix in the index. And I'm going to say create index. Now this create index process is going to basically, create this index for all the 320,000 documents and, in this collection. And it gave me an ACK that it is completed. I'm going to run the same query again, the explain plan, which earlier took about 279 milliseconds. And I'm going to run this explain plan again. Now you can see that an IX scan or an index scan is happening, and the time from 279 milliseconds came down to 0.186. And the overall time from 279, whatever that was, 279 and 674 came down to 0.74 milliseconds. So that's a significant improvement in performance. So again, this is a very simple example on how you can perform query tuning and use appropriate index strategy to optimize your queries for performance. So let's go back to the presentation again now, and let's look at the other best practices. When sized right, you will be able to achieve optimal performance and cost when using DocumentDB. In this section, we will discuss about best practices to size your DocumentDB cluster. So, the vCPU or the compute capacity and the memory per instance determines performance. DocumentDB provides a range of instance classes to choose from, as you can see on the left-hand side of the screen. And the best practices here is to ensure indexes and working set fit in cache. So pick an instance that can host your indexes and working set in memory, right? And also be aware that cache size is, that is available for your working set or your data and index is 2/3 of the available RAM. So if you take like, a 384 gigabyte machine like here, 256 GB is available to you, and the rest is used by the DocumentDB processes, right? So when it comes to selecting an instance, the best practice is to make sure the index and working set fit in memory. And when it comes to the number of instances, you would determine that by what your availability target is, right? So if you say, hey, my availability target is just like 2 nines, you can be happy with just one instance, right? Again, the recovery time in this case is about 8 to 10 minutes, because when that instance goes down, it takes about 8 to 10 minutes for a new instance to be provisioned and be available. And it's fine setup for a dev or test kind of an environment. But in production, you may like say, hey, I want like 3 lines of availability. So you can go with 2 instances where you'll have one primary instance and another a replica instance distributed across 2 AZs. And in this case, if the primary goes down, the replica will be promoted to primary in less than 30 seconds. So that's your recovery time. And if you want like 4 nines of availability, then you can go up to 3 instances, right? So with 3 instances, you get 4 nines availability, where basically your configuration is going to be 1 primary and 2 secondary instances, and you'll have these distributed across 3 AZs. Again, the recovery time is going to be the same, less than 30 seconds. Now, if you add more instances, your availability target is not going to increase. So when do you add more instances? It's generally you would do that if you want to support more read throughput, because this is scaling out, right? So the scale out architecture, you can say I want to support, like today I'm supporting 200,000 reads per second. I want to go to 400,000. Then you may probably want to add more instances if you're already using max of the compute and all that stuff. So again, you would to summarize, the best practice is to select an instance where the index and working set can fit in memory. How many of those is going to be determined by your availability target. Okay, it's demo time again. In this demo, I will show you how you can use a sizing calculator to determine sizing. This tool that I'm going to show you in a bit is built by the DocumentDB Specialist Solutions Architect team and is not officially supported by AWS. I want to call that out so that when you're using it, you know where to go for support, right? You can ask us on the forums or on Twitter or anywhere. But if you go to cloud support, they are not going to be aware of it. So let's go back to our demo here, right? I'm going to go back to the browser, and I'm going to go to that tool. It's available here, and we'll make this link available to you. So again, all the warnings that I just mentioned is written over here. And again, the purpose is basically to give you a good estimate on and ballpark pricing. Again, this is not a substitute for performance testing, right? So here, what I'm going to do is start with a few documents. I'm going to start with about 10 million documents. So let's use this option over here to say 10 million documents, right? So I guess that's 10 million, hopefully. And I'm going to say the document size is 1024. And I'm going to say that the total number of indexes in this collection, again, I'm just giving you an example, right? I have let's say 4 indexes, and the index size is, whatever, 200. I'm just going to add some zeros here. And again, this is just for demo purpose. Right? And I'm going to say I want to host all this index in memory. I want to host all the data in memory as well. And when it comes to, again, this is basically you're giving the data characteristics. Let's say I want to do 200,000 writes or inserts per day. I want to do like 100,000 updates per day, and I want to do 50,000 deletes per day, and about, let's say, 500,000 reads per day. Now I will say the backup, I want to keep the backup for about 7 days. I'm going to be running this in Northern Virginia region. So when I say submit, this will tell you that you need R5 8x large, and it's going to cost you so much. And it'll by default give you 3 instances because that gives you 4 nines of availability. But if you don't need 4 nines of availability, you can always reduce that. Right, so I'll talk about the pricing dimensions and other stuff in a bit. The other components here are from the pricing dimension. Again, if you're coming from a MongoDB world, you can use this option too, where you can run the sizing JS on your Mongo cluster, and you can then populate that data that this returns into the sizing questionnaire, populate some additional information about your workload, like read throughput and write throughput and so on, and upload this file and say submit. It'll give you a similar output that you just saw, like this, and it will give you what instances. Again, this is a good place to get started when it comes to sizing, and then you can start doing performance test on top of it. All right, so now let's go back to our presentation, and let's look at the other best practices we had planned for today. So we saw how you can connect and query efficiently. We also discussed about how to size your cluster based on the data characteristics. Now, these data characteristics do evolve over a period of time. And now imagine that your workload grows and you need to support higher data volume and read and write throughput. And this is a very common situation we see for our customers. And when you have to support those higher throughput, it's important to scale. So in this section, we will discuss the best practices to scale DocumentDB. Let's start with read scaling. Let's say you want to scale your 3-instance or 3-node cluster to support higher read throughput. How do you do that? It's very simple. You scale reads just by adding read replicas. You can add up to 15 read replicas. And when you use the read preference as secondary preferred, remember we talked about it in the first best practice, right? The driver will use those new replicas automatically. So there's no application change required whatsoever. And sometimes you need both levels of consistency. We've been talking about read preference, secondary preferred, but what if you want to read the data, like you want to read your own write consistency, right? You can set the default as secondary preferred, and on a per query basis, you can override, right? So as you can see in this example, the default is set to secondary preferred, and for each query, depending on which queries require stronger consistency, you can override and set the value for read preference to primary for those queries alone. Right? And now, we talked about read scaling. Now let's talk about write scaling. Right? Let's say our write throughput has increased, and we need to support a higher writes, more number of writes per second. Right? So we need to scale our cluster that right now, as you see in the slide, has about 3 R5 large instances, and you want to go from this to R5 4x large. How do you scale? What are the best practices to do that, right? So you start by adding 3 R5 4x large instances, the target state that you want to reach to, and then you trigger an auto failover. And I'll show this to you in a demo on how you can do that. And this large instance, will automatically be selected as the primary. So when you trigger an auto failover. And once you do that, now you have like a 6-node cluster with 3 large instances and 3 small instances. You can technically, start sending your writes. So your writes are already scaled, right? But you do not need those smaller instances anymore. So you can delete them to complete your scaling process, right? So now you are left with 3 R5 4x large instance. So your primary instance is now scaled from R5x large to 4x large, so that it has more compute. And yes, we also scaled your replica instance because we recommend that you have an homogeneous setup, so that if this primary goes down, then the replica it picks also will be of the same size. So you can always have a guaranteed SLA then. Let's discuss about storage and I/O scaling. We saw read scaling, write scaling. Now let's talk about storage and I/O scaling. Well, there is not much to discuss here because storage and I/O scales automatically in DocumentDB. Right? Storage is scaled in 10 gigabyte segment all the way up to 64 terabytes. And one thing to be aware is DocumentDB does not shrink storage. So it basically follows the high watermark model. It will use the vacated space before allocating new space though. So the best practice again here is when you're migrating large data set into DocumentDB, and if you're intending to delete most of it, like if let's say you have historical data that you're thinking I'll migrate into DocumentDB and then delete it, we recommend that you delete it and then bring it in so that you're not charged for based on the high watermark model. And here are some of the metrics to monitor when it comes to scaling, right? The first two are the buffer cache hit ratios and index buffer cache hit ratios. These tell how much of data is accessed from memory versus disk. We like to see this around 95% mark. And if it goes below that, see what is causing it. Is it because of organic data growth? Then scale up to have more memory. If not, see if you can purge old data or remove unused indexes. And the next two metrics are pretty standard: CPU utilization and freeable memory. If you see the CPU to be pegged at 75-80% or continuously, then see if there is a need to scale up. Freeable memory, if it continues to drop, again, either delete unused data like unused indexes or older data, or scale the instance up. And then database cursors and the cursor timeout, right? So you can look at the cursors. There's also another metric that probably you can look at is connections. So these metrics like connections and cursors are also dependent on the instance size. So the number of connections, for example, supported by the largest instance is 30,000, and the max number of cursors supported by the largest instance is 4,560. So if these and the smaller the instance, the less is the number. So if you are using more of these cursors and connection resources, you can monitor those and scale as needed, or close those unused cursors proactively, and use optimal connections. Like be frugal in how you create those connections. It's demo time again. In this demo, I'll show you how to perform write scaling. Let's go back to the AWS console. So I have the regional cluster getting started with DocumentDB here that we were playing with. And this originally had only 3 instances R5 larges. And what I did is I pre-created 3 R5 4x large instances. The reason I pre-created is it takes about 8 to 10 minutes to save time during this webinar. Thought I'll just create those instances before time. And now I have those. So I have like a 6 instance cluster where I have 3 R5 large and 3 R5 4x larges. And to scale, now I need to basically trigger an auto failover so that the primary instance, which is right now pointing to an R5 large, will then point to one of these R5 4x larges. So how I trigger failover is I go here, say action, and say failover. And I'm gonna say yes, I'm sure, and say failover. This process takes about 30 seconds or so, or less, and you would see that the primary instance will then start be pointing to the larger instance. So we'll come back to this. Let's go back to our presentation. I'll finish the next best practice and show you that the primary instance is now pointing to the larger node size. So far, we discussed the best practices to develop and operate DocumentDB, which is like connecting, querying, sizing, scaling, and so on. In this final section, I will discuss how to do cost optimization. So to discuss about cost optimization, it is important to understand how you will be charged, right? What will be the cost that is generated. So there are 4 pricing dimensions in DocumentDB. It's instances is one of the dimensions, IOPS, storage, and backup. IOPS is the dynamic variable here, right? So in this section, we'll dive deep to see what sources contribute to IOPS and how we can optimize IOPS cost. Because with sizing, you'll obviously be on an optimized instance cost. So how can you minimize your IOPS cost? Right? So any operation between your compute instance and storage layer will result in IOPS. And each document, let's say read or write, can take when you're performing read or writes, it can take more than one physical I/O depending on the document size. So the sources for this I/O, as you see on the slide here, includes write to or reads from storage, index scans. When you create indexes, those create IOPS. When you perform updates, those do IOPS. And there are like soft deletes due to the MVCC write patterns we use. So all those generate IOPS. And it's a good practice to estimate your I/O usage by benchmarking your application and DocumentDB cluster and observe what those IOs build are, right? And then monitor the IOPS usage in the billing dashboard, set alarms for 50% and 75% of your estimated bill. So when you benchmark and this is what I'm expecting, and if you see that alarm goes off like at the 50% alarm, let's say you expect $10,000 as a bill, and you expect the 50% bill to go like alarm, which is 5,000 cost to meet around the middle of the month. But if it goes way sooner, something is wrong. So you can be proactive about it and go and do some research to see what is causing it. And if it is IOPS, let's see how you can tune the IOPS, how you can optimize the IOPS. Right, so we'll look at it from an index, query, and sizing and collection design perspective. So when it comes to index and query, right, Amazon DocumentDB does not support compression for stored data or indexes. So be frugal when it comes to creating indexes and remove the unused indexes and optimize the indexes. Right, for example, one compound index is smaller than multiple single indexes. And when it comes to TTL deletes, be aware that they do consume IO. So to minimize the IO cost, you can create a new collection. We call it the rolling collection. You can create a new collection at a desired interval. Like, let's say you create a collection on a per day basis and write your records into them, then delete the whole collection when it has expired, right? So instead of like saying, okay, delete the document on a daily basis, just drop the entire collection, right? The downside with this approach is you will have to, send separate queries to each collection if you have to do queries across those collections. But it does save IOPS costs. So again, you'll have to make that trade-off, right? It's efficient with respect to IOPS, but with performance, you'll have to probably do joins. So if that is, again, you'll have to evaluate this on a use case by use case basis. And then optimize queries that are not performing at a desired SLA, right? Because if you're like, for example, we saw in the demo, we saw collection scan. Avoid using those collection scans or union scans, right? DocumentDB does support covered queries, which is, you'll see that as IXScan only if you look at the explain plan of the queries, right? And this will leverage indexes for responding to the query, and it'll use index scan or index only scan. You'll perform less scan and hence less IOPS, right? If you're hitting the disk. And when you're using sort, like we saw in the demo, use the sort keys as this index suffix so that again the scan can be minimized. We talked about sizing, right? So again, just to reiterate, instance sizing best practices to fit index and working set in memory, and set aside 1/3 of the memory for DocumentDB control plane process and 2/3 for your data and index. And determine your instance count by the availability target and also your read throughput. And when it comes to collection design, right, DocumentDB is ideal for OLTP type of workload. So it's a best practice to define your retention period and delete older documents. The per collection limit is about 32 terabytes, but it's recommended to keep it around 5 terabytes for efficient data management and index management. And if the collection grows unbound and the reads and updates are always to the most recent documents for your workload, then use smaller collection by moving the older data to different collection, because this approach will help maintain the recent data in memory and also avoid updates to large number of documents, right? Because when you break the collection into multiple collections and you're only accessing the most recent one in your workload, if that is the case applicable to you, when you're writing into it, it's only going to update small portion of indexes as opposed to a monolith collection with which is updating indexes for all the older documents as well, which is not required probably, right? So and that will help you save IOPS. So breaking your collection, a monolith collection into multiple smaller collections will help with optimizing IO cost as well. And then, with DocumentDB, you can start and stop a DocumentDB cluster, right? This is a good option for dev and test scenarios where you can turn them off during a weekend and you will not incur instance charges when you stop the cluster. Your data is still stored in the cluster, so there will be storage cost. Backup cost will not increase because the data is not, there's no incremental change to the data, because the primary instance and all the instances are down. And you can always, start the cluster whenever, you come back on Monday, for example, in the dev test example, and, you'll start, accumulating the charges from there. In this final demo, I will show you how to stop a cluster so that you can save cost when you're not using a DocumentDB cluster. Let's go to the AWS console. And before I show you how to stop a cluster, I wanted to make sure that I close the loop on the previous demo where we scaled the writes. So we added, I actually pre-created the R5-4x large instances, and I initiated a failover. And that failover process completed. Like I said, it takes about 30 seconds or less. And now the new primary instance is our R5-4x large instances. So that's basically the expected outcome because we wanted to scale our writes up. So, technically speaking, now you can delete those smaller instances as you no longer need them. But let's switch to this demo on cost optimization and how you can save cost by stopping the cluster. It's pretty simple. You just select the cluster, go to the actions option, and say stop. And this will give you a warning in that it can stop a cluster for up to 7 days. And if you don't start it again, like within that 7 days, it will be automatically started. And we do this so that we can apply security patches and so on. You can certainly come back after 7 days and stop it again. You can stop it as many times you want. I'm going to say accept that warning and say stop cluster. And this process will take a few minutes to stop this cluster. So in a bit, you would start seeing the status to go to stopping, and one by one, all the instances will go to stop status. And once all the instances are stopped, you can certainly come back here and go to actions and say start. So since it's going to take about 10 minutes or so, I'm just going to skip the part where you can see the stop status. But one thing I wanted to add is you don't have to do this operation through the cluster. You can also do it through CLI command so that you can script it. So on a Friday evening, just run that script to stop, and then on a Monday morning, just run the script to start. So that's about how you can stop the cluster and save cost. And that was our final demo. So before I wrap up, I just wanted to give you some links and resources. So the first one over there is points to our customer portal. You can read about customer case studies and codes. And if you want to learn more about DocumentDB, the resources link over there, the second one would be really good. If you want to get your hands dirty with DocumentDB, you can participate in our self-service workshop, and the link to that is provided here as well. That brings us to the end of this webinar. Thank you so much for your time and attention. Please stay safe and take care of yourselves.